All right, well, welcome everyone to the SEG Near Surface Geophysics Technical Section Student Subcommittee's second webinar on Resipy, which is part of our webinar series on open source software. The SEG Near Surface Student Subcommittee, as well as myself, will serve as your host for today's webinar. Before we begin, as Lori has thrown into the chat there, the model for this webinar will be presentation with some hands-on exercises that people can work on with some examples. We recommend people please already have the software downloaded and ready. For those of you all who joined us for the first one, hopefully managed to kind of start playing around with Resipy in the meantime. Afterwards, there'll be an extended Q&A session during that time, or as Cinna is going through his presentation, feel free to throw any questions you have into the Q&A box. That way, after everything is done, the recording will actually capture all the questions in the Q&A section. Anything that's thrown in the chat just vanishes. So please, any questions, please make sure you throw that into the Q&A box. During the actual Q&A session itself, if you'd like to ask any questions, you can also raise your hand in the webinar interface, and we will adjust your settings that allow you to unmute and ask your question directly. Today's presenter is Cinna Sanayan, once again. Cinna is a geophysicist who research mainly focuses on near-surface environmental and engineering problems. Cinna has been an active member of SEG since 2015 and is currently an assistant professor of environmental geophysics at the School of Geosciences at the University of Oklahoma. He holds a bachelor's in mining engineering from the University of Tehran and a master's in science and petroleum engineering from Sharud University of Technology, and a PhD in environmental sciences from Rutgers University. His postdoctoral research was on the assessment of soil deformation and failure with complex electrical methods. Cinna's current research builds upon his initial goal of bridging geophysics and engineering. Cinna is aiming to show that geophysical methods can be used as reliable characterization tools for monitoring natural hazards, and potentially can be used as effective geohazard prediction tools in the future. He is an experienced geophysicist and knows a wide range of geophysical techniques. Is also one of the primary developers of Resipy and a lot of other stuff associated with Resipy. So without further ado, I will hand things off to Cinna to get things started.
Thank you very much, Chris, for the nice introduction. Today we were supposed to be two people. Jimmy Boyd was also supposed to join us. He's the mastermind behind all the complex meshing, specifically for the 3D problems. But unfortunately, he had another obligation and he can't join us. So I'll try my best to cover his part. He made some slides for me, but we'll see how it goes. I'm not the mesh person because I always use the meshing part. Anyway. So I will not show any presentation that much today initially, because I think everybody from the previous 2D session, Resipy 1, already is familiar with the software, hopefully. So I'm just diving into the 3D immediately right now. And if you have any questions or regarding the previous webinar, that something that was still vague, please let us know. Before going to show you how it works, one thing that I always recommend is that always update to the newer version. I myself was not used to do that. Software, if they work, I never update them. But as a developer now, I know there are bugs here and there that we fix them always. So please update to the latest version, which is 3.4.5 for now. There are several issues that have been resolved with specifically with meshing and some visualization in 2D and 3D. Hopefully that helps out. Okay, let me share. I better share my portion of window that has the software, right? I think that's better. All right, I hope that you see my screen well enough. Or when you open the software, you already know that it starts from 2D inverse problem, and a lot of options. So I'm going to show you a simple 3D inversion. To do that, you have to select this 3D radio button in here. And once you do that, the visualization screen turns dark. That's how we show the 3D better instead of a white background. I'm gonna start with the simplest example that we have, which is a flat surface, everything. So file format, protocol DC, that stands for resistivity, direct current resistivity. I'm not changing anything like that. And then import the data. And by default, you will be directed to the examples directory that is supplied with the software. So you don't need to download any extra examples for this webinar. And in there, I'm gonna select the DC 3D, okay? And open that. In there, you see a protocol.dat file, you see a protocol reciprocal file and a forward model. Let's stick with the simplest one that says protocol.dat. So once you open that, something weird will look like some stuff that are like upside down. We put this way so people know that they have to definitely change their electrode topography, because people sometimes just import and try to invert it, that causes problems. So immediately after importing, something weird is shown because you have to definitely define your electrodes. This is the most important thing for the 3D inversion, 3D forward modeling. Unlike the 2D that usually is a line and everything simple, this one requires a better attention. So most of the files in 3D, they can either have a bunch of lines together or have a non-uniform grid, meaning that all the electrodes can be scattered all over the place and it doesn't matter. For this specific example, we have a few lines that are combined into a 3D survey. And if you look here in the label, you see two numbers, basically one number, a space, another number. The first number is the line number if you have line or a formatted grid. The second one is your electrode number on that line. So if I go down, I see my line number 1 has 25 electrodes. And then line number 2 might have different, might not. So again, 25, and line number 3, 25. It doesn't matter if your lines have different number of electrodes. The thing that is important, if you have a formatted grid, you always have to define the line number and the electrode number. So if your line 3 has 50 electrodes, then you will continue this to 50 electrodes. The software may not know that. As you can definitely see in here, this is a completely weird thing, and because Resipy doesn't know your formatted grid, specifically for certain format files such as protocol that doesn't give you anything about electrode configuration in there. So you have to define the X, Y, and Z of your grid or your individual electrodes, and also if it's a buried electrode. So for that, I am going to open in the same folder, automatically opens that one, and import the electrode.csv. That is the one that gives you the available electrodes. So once I do that, it's already populated correctly. It has all the X, Y's, and Z's. This is a flat survey, so no topography. All the Z's are gone. Just to show you the format of the imported file for this specific example, I'm gonna stop sharing this one and probably share my Excel file on that. Let me figure out how to do that. This is a CSV formatted file. I'm showing it on Excel, but a CSV file can be opened with any text editor, right? The best way to do that is in Excel, in my opinion, and then save it as a CSV format. You need to have, always you need to have for 3D, you need to have the label, X, Y, and Z, at least to have a 3D grid set. And then you can import that. But probably you already know that. You can also copy and paste any of these columns that you like, and then just basically paste them into here from first electrode. Simple as that. Just to show you how it works, I'm gonna make all the X's 0 and copy, and then come here and use Control V as a paste, and it just pastes it. And you can just import that. That what is important that you need to have the headers for each column. So that is really important. So you can't just import something without the headers. You need label X, Y, and Z as a header. It doesn't matter if it's a lowercase or uppercase Z, X, Y, Z. I think it matters for the label though. Anyway, so that's the format of the file. Again, stop sharing. Back to the software. Okay, so once you do that, you can come back to the data section, and now you can see, okay, this is completely normal. This is a 3-line survey with a combination of measurements between 2 lines, so a full 3D inversion, not just each line individually surveyed. And you can actually contour this if you like as a pseudo 3D contour. And also sometimes in 3D, you have a non-uniform grid, unlike this one, that electrodes pass over each other at any weird location. And in that scenario, if you have really close electrodes that are very, very close and cause problematic meshing problems, you can merge those very close electrodes together and make sure that doesn't cause any problems in the future. So once you do that, I'm not going to go through any of these, just going to show you that's the 2 important things for any 3D inversion: importing the data, electrode definition, and then you can simply invert that. Resipy by default will create a mesh based on the electrodes and invert that data for you. So again, in here, you have a lot of options to visualize this for yourself. The first one is obviously selecting the file that you imported. You can import multiple files as a batch inversion, like the 2D inversion. Also, you have the resistivity, log 10 resistivity, sensitivity, and so many others. And like the 2D, you can select the minimum and maximum of the color bar. So they should match the numbers in here. So if it's a log resistivity value, so I'm going to show anything from, let's say, 1.9 in here to 2.2 and apply. Okay, something strange is going on. Okay, I guess I found the bug. Maybe we have to convert them to resistivity. So 10 to 150. Yep. Okay, so you have to convert them to resistivity if you're using resistivity log 10 or the resistivity ohm meter. That's a thing, which is easy. You just use a calculator. Anyway, I'm gonna convert that to jet, maybe showing the colors better. In here, you can, like 2D, you can show the edges if you like, but you have some other options in here that are just for the 3D inversions. The threshold in here, unlike the minimum and maximum that changes the color bar, in here will only select the part of the 3D mesh that you are interested in. So if I want to show anything from, let's say, 90 ohm meters, sorry, this one probably it's not like that. So let's try. I'm sorry for this, but now I realize there is a problem. 1.9 to 2.1 and apply 3D, you see that some parts of the mesh are gone. I can make this even narrower and see how it will look like. So some part of the mesh is now gone, right? This is really great because this allows you to calculate the volume of the remaining cells. If you have an anomaly, let's say I have this basically greenish area. This is my anomaly that I'm really interested. So it's probably above 2.1, 2.15 maybe. And I will click on this one and apply, and it will give me the volume of that region that is inside the mesh that we saw. So if I make it even smaller, then it will become even lower than that. So you see, this is the volume of only this one that is available in here. And this is really great if you want to calculate the volume of your anomaly that you have, whatever kind of a mineral deposit or something like that. All right. Additionally, you can slice this along the any kind of X and Y and Z axis you like. So for that, I'm going to turn on the grid so I know what numbers I'm dealing with. Let's slice this at 18. So passing over this anomaly in here, x-axis 18, and then something in the middle for y is equal to 0. And we want to see something at, let's say, maybe 5 meters. So -5, and apply 3D. Now you can clearly see the anomaly as the slices in here. I can zoom in to see better. You can make it a contour format file if you like. And the contour in here is actually the Delaunay 3D filter, not an actual contouring, but it is visualized in the form of contours. That's why we don't call it a contour. The problem with Delaunay 3D is that if you have topography, it will not work as well. So it's really good for flat surveys or cylinders or tanks or something like that, but not when you have topography, because it connects all the dots together and give you a block. Hopefully we're going to show how that's going to cause problems later on. Another good option that you have that is good for surveys that are not uniform grid, on uniform grid, is a slicing along the electrodes. Let's say you have a waterborne survey and you have the boat following a track and going back and forth on certain grid, then you can slice it along the electrodes. For this one, doesn't really look well, because this survey starts here from electrode 1 and goes all the way down here, and then the last electrode, instead of being like a snake, it comes down here. So you see this weird connections. But if this wasn't the case, you would have seen just slicing the mesh along the electrodes. So that's good for certain type of meshes. And obviously you can again save the data like any other saving that you want to do. And I'm gonna select desktop for here and create a Resipy 3D webinar and save the data in there. What it does is saving a bunch of files, including the inversion files, the grid, the mesh, the imported file, but the format that Resipy later on can read better, as well as a important thing called a VTK file. This VTK file is a universal format that can be opened in a lot of software, including open source software called ParaView or Visit. These can import VTK. So I'm going to show you how that one works. Stop sharing here and start sharing my entire screen this time. Okay, so ParaView, maybe some of you are already familiar with it. It's a software for visualization. It looks like that. I'm just going to show you how you can utilize this for better visualization for your purposes than using Resipy alone, because Resipy is slightly limited for visualization. So I'm going to go here into desktop, Resipy 3D webinar, and in here you can see there is this protocol.vtk file. This is the file that you want to import into Resipy. There are also your working directory, including all the import, export, error, as well as this important this important file, which is giving you the data points of individual cell centers and the resistivity and log resistivity values. This can be used for contouring on your own with Python or any other software such as Surfer. But for ParaView, all you need is this guy. So you just drag and drop it here, and automatically it will populate and show you what you have in here. Now the default is not selected on the right format, so you need to do a little tutorial on the ParaView. but you can select log 10, then it will show you exactly the same thing that Resipy was showing you. For instance, I can select the jet as well in here, and I will see like that. So here you have a lot more to do compared to Resipy. There are a lot more filters that are available to you. One of the things was the Lane 3D, for instance, that we used over there, but there are so many others that you can use. I always suggest my students and colleagues to, for any purpose, reporting or publication, using ParaView instead of just the default things that Resipy gives you, because this has a lot more capability compared to Resipy. And the fun fact is that behind what you're seeing in Resipy, the visualization that you see in here, we have a mini ParaView called PyVista package that is doing what is the ParaView can do a lot better. Okay, I forgot here, you can also make isosurfaces, basically just surfaces that you like to show for certain resistivity values. For instance, isosurface show me a resistance 2.1, and then another isosurface at 2.2, and then another isosurface at 2.3 maybe. And always you have to separate any numbers with a comma. So decimals always separated with a dot, and numbers or values are separated with a comma. That's how it is with Resipy. And it works for slices as well. So you can have many slices. You don't have to just have one slice at each axis. And they are all separated by a comma. So if I do that, I clearly see like a bunch of isosurfaces in here. So 2.1 was around here, and then there's 2.2, probably 2.3s inside and not really easy to see. So maybe we just remove it and see if we can't see anything. Oh well, 0.3 doesn't really exist. Okay, so, and that's how the basic 3D inversion for surface arrays work. What you need to, again, take into account is the electrode XYZ topography tab. That is very important, that you always have to deal with for any 3D inversion. Unlike the 2D, you need to do that. And unfortunately, this one only works. You can also use that if you have a let's say formal grid, the part that here that allows you to create the survey. But sometimes it's iffy. For instance, in here it says you have 75 electrodes, right? But that's 3 lines, each 25. So if you use that and define 3 lines in here, okay, and correct line spacing, whatever you like. If you do that, it will give you 75 electrodes per line. So it doesn't always work. You need the best, your best option is to always manually use Excel or something and define your electrodes, at least for a grid. So see, that's how weird now it looks like. Okay, I'm gonna go back here and re-import this data set. Oh, and also if some part are missing for the topography, for instance. So this electrode partial in here, if I open that, there's some missing topography in here. You can use the interpolate missing topography, and automatically it will interpolate the topography for you. So this one has some weird topography going on, right? And then it automatically got populated linearly based on the available topography values. So similarly to 2D, you will have the option of pre-processing. It is slightly limited compared to 2D. So you no longer have the pseudo section to collect on individual points and remove them, because in 3D, it's almost impossible to do that. So click on anything inside this. So we don't have that option, but you still have the option of basically range filtering. So this file doesn't have any reciprocal measurement, so you don't see any error histogram. That's why it's all blank, and doesn't have any phase values, resistance error model, and basically phasor model either, so all of them are gone. But still, you can filter based on a certain apparent resistivities if you like. I would highly suggest that you look at this scale in here, and if there is only one really large value or one small value, you can clearly remove it in here. And then you have the very important part of this software, which allows you to create a mesh based on your own characteristics. This is the most important part, in my opinion, because it allows you to basically change everything. But if you just want to invert your data, the default values are already there, and you don't really need to change anything. I'm going to start with the characteristic length. This will be the distance between individual nodes at the surface, okay? And usually is a half of the electrode spacing. For uniform grids, it's easy to calculate. For non-uniform grids, it becomes slightly more difficult, because if you have electrodes that are really close to each other and electrodes that are really far from each other, that will mess up everything. So what we do, we usually find the minimum spacing, and then half of that will become your characteristic length, basically the distance of how small the cells will be at the surface. This will be problematic if you have really close electrodes, because your non-uniform grid did not really account for a spacing, and now there are two electrodes that are really close to each other, and then your characteristic length will become really, really small. And let's say you have a very large survey, and then you kind of cross line over each other, but not perfectly, and your mesh basically becomes impossible to create. And then you get either you get an error, or you get like a 2-hour time to create a mesh. So I highly suggest that if you have such really close electrodes, you just merge them together, and that would be a 0.01 average of the multiplied by average electrode spacing. So those are that are closer, that distance will be merged together. So, but also you can actually define your own characteristic length. You don't have to do the default. Whatever you like, you have a coarse mesh, you put a large number in here. You want a small mesh, you put a small number in here. One thing that is important, it will be problematic if your characteristic length is more than the electrode spacing, and then it become difficult to put the nodes on the electrodes. So in here, for instance, if I go back to my electrode topography in here, the spacing is 2 meters at the surface between the electrodes, right? And 5 meters between the lines. So minimum electrode spacing is 2 meters. What it does, my meshing by default probably makes something that is 1 meter spaced apart in here. So there is two, as you can see in here, if I zoom in, there are two cells in between each two electrodes. So if I want to make this finer, I would have to make something even smaller. So 0.25, for instance, or let's say 0.5. That would give me 4. 1, 2, 3, 4 in between each two electrodes. So 1, 2, 3, 4, right? So if you want to make it coarser, you make this even bigger. So if I make it 2, exactly as the same as the electrode spacing was, you can see there is one element between each two electrodes in here. Another thing is the growth factor depth. This is the multiplier factor that how large the cells at depth of visualized mesh will be compared to the surface. So 8 in here means that whatever is the size of this one, which was 1 meter in here, 2 meters in here, this one at the bottom in here will be 8 times bigger than that. So 16 meter, right? This growth factor from depth always compares this part and this part. And then basically everything expands in between. The growth factor surface, on the other hand, is how the electrodes, how the mesh cells will expand in between the two electrodes or two nodes in here. Now in here, we don't have that much of the, we put exactly as the same as electrode spacing. So everything is, there's no more room for expansion. So if I make this small, let's say 0.25, for instance, and use a large growth factor in here. Ideally, it should have expanded this one, but it doesn't. So I think something is not right. I have to ask Jimmy. That's what he told me it should happen, but it's not happening. Maybe I have to optimize the grid. This 0.5. Or maybe that's for a non-uniform grid. So this is where I needed Jimmy's help. Okay, but anyway, this one is telling you the distance, how the nodes, how the elements should grow after the smallest close to the electrode, away from them at the surface. That's what this one does. So if you want to, if you don't have confidence in your data in the between lines, for instance, you will increase this number to have larger mesh cells in that region if you don't have data in there. If, okay, let's put this back on 2 meters and 5 is all good. All right, so if you want to keep the same format in your grid, but just make the cells smaller, you can use this refine checkbox. This will allow you to basically divide individual cells in here, you can see, into 2 or 3 different cells. So if I do that, the format will be the same, but the cells will be just smaller. So still have the same big, for instance, mesh element size, but they're smaller. That's what the refining does for you. So now you can see the between 2 electrodes. Prior to this was just 1 element, now it's 2 elements, so divide everything by 2. Okay, and sometimes you import a mesh by this drop down menu and you import your custom mesh, and it's not optimized. You can use the optimize for grid option in here, which basically the refinement of a non-uniform grid will be correct for the survey. This will enhance the inversion time significantly. And the fine coarse boundary depth is telling you how deep your mesh can see. Default is calculated. I don't know, I don't remember off the top of my head how it calculated. Oh, it's 2/3 of a maximum dipole you have. But if you think you can see deeper, or if you think you don't see as deep, then you can change that. So in this one is looking like around 17, 18 meter. I can change that to 25 and create my mesh. And now you can see all the way to 25 meters, or you can make it even shallower, 5 meters. So this is just to allow you to basically define the bottom of your mesh. And basically this growth factor now is a function of this. So every time the bottom of the mesh that you see is 8 times bigger than the surface. So if this one is really deep, your mesh automatically becomes much more smoother. Okay, so this is for the meshing and what the capabilities you have for the inversion of the surface meshes. And we don't call it a surface mesh. This time we call it a half space mesh, because this is just from the surface all the way down, and there are part of mesh that are not shown in here. But there are other options you have, like creating a tank mesh that is confined at boundaries around the electrodes, or any boundaries that you like. So this mesh, as I said, is not confined in here, despite the fact that it's not shown in here. We have more cells going this way, that way, and that way. But the tank mesh is definitely confined to a boundary that you define. If I go there, it will allow you to define again a characteristic length, but then you also have to define the origination point of the tank, and then how it goes all the way. So you define a point and then you extend it to create a tank from the surface, for instance. Let's see if we can do that with this one. It looks like weird right now. Yeah, it's not defined for this type of measurement. And you also have the option to create a cylinder or a column mesh if you have a cylinder survey, like a column or something like that in a lab experiment. And also you can import your custom mesh, which should be in VTK or dot mesh made by Gmesh, or VTK that is created by ParaView, or a .dat file, which is the default format for inversion code behind Resipy R3T. All right. Okay. So this was the basic of the 3D inversion at the surface. Let's do some examples of let's say the tank experiment. So again, I'm going to go to examples. There is a 3D cylinder in here. I don't know what's the file format in here, so let me figure that out for you. Oh, that's a 4 model. Okay, we can do it later. All right, so let's do a tank experiment then. That's also a forward model. Okay, so let's do some forward modeling in here, because we have a lot of forward models, but not that many inversion examples, apparently. We have a 3D column one. Okay, we have something. Let's see if that works. So if we go to example, if you go to 3D time-lapse column, you can open this protocol.dat file. Again, definitely looks strange, right? And then you go in here, and the same column, you import the electrode file. And now you have all the correct topography and everything. Go back there, you can clearly see this looks like a column experiment, right? So a couple of things in here that are really important that you may want to note when you're creating a column. Resipy by default will try its best to define the bounds of this box around your cylinder, but it might be difficult for it to correctly define the bounds. And if you incorrectly define the bounds during the meshing, the mesh will not be defined correctly. Let's see if this one works just fine. So if I go to cylinder in here, and it gives you a bottom and top of your column, and a growth factor which goes inside, and a characteristic length like this one. Let's create this mesh. Well, it works just fine. This for this one. So notice that the mesh is extended slightly above the first part of the electrodes, and also extended slightly below the last part. So I think it's actually this way. Because if you define your surface in here at the surface, and your bottom at the very bottom of the electrodes, for some weird reason, the mesh becomes hollow. If you see a hollow mesh, or you see a fully black side to the mesh, this means that your mesh is empty and it's not going to work out. So you should not invert that data. For this, let's give it a try and invert it and see how it looks like. So invert. Hopefully that's going to invert quickly. Yeah, it did. So again, like the other 3D meshes, you have the option to see all the parts of the mesh. Again, I'm pretty sure it starts at this part, because that's 0.2, 0.3, 0.4. And the bottom of the mesh, yeah, and it cut the bottom of mesh at the bottom. If you don't want that to happen, you can always go back to the inversion settings, advanced, and say do not crop the output. And now everything is full and intact, okay, based on your column. Again, you can use all of these options. Out of curiosity, I'm going to use this slice along the electron and see what happens. Yeah, so some weird stuff happens, but it might work for you. Anyway. Again, you can also compute any attribute that you like, basically any empirical equations you might have that requires resistivity or induced polarization or a combination of both to give you a result that is not calculated by default in here, and you do that. And again, I have to emphasize that you always need an x before the defined parameter. Okay, so this example in here is not really correct, unfortunately, because the parameter is either resistivity parentheses ohm dot meter or resistivity parentheses log 10. So if I just use this as calculating for the conductivity, which is in here, it will not work. The correct format for this is 1 over x resistivity ohm m. Note that I put the resistivity ohm meter into quotations and also inside a bracket. This is also the part that you have to do. This has to be inside a bracket, following exactly the things that you are seeing in here, and inside a bracket with an x before it. So this is basically telling you 1 over resistivity, which is equal to conductivity. I'm going to call it con dot just to make sure that it's different than the one that is already computed. And if it's successful, it tells you that it's successfully computed and it's added in here so you can calculate the conductivity. If I remove anything from here, if I remove the x from here, it will be unsupported, not working. You need to put that x in there. Okay. Let's see what questions we have. There are many questions in here. So Elaine said it's not a bug. You had to set it to log. Okay, thank you. I think that's a long time before. Anyway, kidoki. Let's do some form modeling in here. You can do that. It's limited in the GUI, very limited, but it is doable. So to do that, I'm going to select 3D forward in here, and everything in here is blacked out. If you want to do a 3D forward model with induced polarization, all you have to do is just check this one, but let's keep it simple for now. And in here, you either can use this function to generate a bunch of lines for yourself, or you can define your grid however it is, based on any mesh that you want to create or any mesh that you already have created, and then import the electrodes. Doesn't matter. I'm just, again, gonna keep it simple. So 4 lines, spacing of 4 meters, electrode spacing 1 meter. Each line has 24 electrodes. I will generate this grid for myself. Okay, so each line has 24 electrodes. And for now, no topography. I go to the mesh, like half space, and keep it the default in here for now, and create my mesh. All right, so this is my mesh right now. Okay, and I want to create a 2D. I want to create a 3D anomaly in here. To do that, I have to first click on this one, region mode. And we put this 1, 2, and 3 in here to tell you that always you have to start with region mode, then add region, and then exit mode. For any anomaly you're defining in here, it can be done in different formats. Okay, region mode, once you click on that, you will be given a big whitish box in here with a bunch of handles that you can click on the handles and make them smaller or bigger. depending on whatever you like. So I'm going to zoom in and create a small anomaly in here for myself. Oops. Right. And then I want to move this. I click on the, hopefully the center one, and move it wherever I like. All right, that looks good. Okay, this is my first anomaly in here. So I'm going to click add region. And this was a box that helped you to select the mesh cells that are already there. Unlike 2D that you could have designed your model prior to meshing, this one is not possible for 3D. So it always, your anomaly will not look perfectly like a box or like what you want. And there is no possibility to create an anomaly that is more complex than a box selecting the meshes in the GUI. In the API, you have the ability to do whatever you want. So that's the good thing about the API. Let's give it a connectivity 20 ohm meter, and then zip mode. All right, now this is the anomaly nested inside the entire mesh. My region 1 is this 100 ohm meter red one, and my region 2 is this one. Someone is asking, is it possible to add a spherical anomaly? Unfortunately, as I said, no, not in here. In the API, yes, you can do that. You just have to define a sphere and then select the cells that can be a sphere. Let's add another region. Let's make a different region that is really resistive, maybe far away from that. Okay, that should be enough. Add region, and didn't select anything. Exit mode. Okay, I think we have a bug here. Make it 500, and all right. Then you can go to the formal and define either define a sequence on the lines that you defined, or import a sequence that you already have as a custom sequence, or combination of both. It doesn't matter. Let's keep it simple as dipole. And again, it's explained what a value means in here. And then add 2% noise, and then do a forward modeling. So it's telling you that you have a resistive feature in here, a conductive feature probably in here, and that's how the pseudo section looks like. You can also contour this, or basically use the Delaunay format to look at it. If you have lines, Resipy automatically will figure out there are lines in here. If you don't have lines, that would be there won't be any grayish line in here connecting the electrodes. So this is just telling you there's a line. It doesn't mean there's like tubes or anything like that. So this is your formal model. I can immediately invert that just to look at the inversion. Let's see how that looks like. So I forgot to uncheck this one. That's why you see the whole mesh. That's what I was talking about. Okay, so this is more like it. So again, something is not right, in my opinion, because we've lost the very conductive feature, and now we only have the resistive one, I think. So we got to figure out what's wrong in here. Okay, so this is the forward modeling. You can do the forward modeling on any type of mesh, so it doesn't really matter what type of mesh you have. I'm going to create a forward model on a tank experiment this time instead of doing this this surface inversion. So I'm going to stop sharing and close this, reopen it again. In the meantime, if you have any questions, let me know. Okay. Let's share again. All right, 3D formal. And now this time I'm going to import some electrodes. So again, I'm going to the DC 3D tank experiment and import the electrodes. Okay. And I go to the mesh tab and select the tank. Automatically, it again defines some values for me. I create the mesh. If the mesh looks good, we're good. If it doesn't look good, you have to change these values. Again, the origin means 1 point of the mesh. So this one is 0, 0, 1.6 at Z. So that would be here, right? 0, 0 at depth of 1.6, somewhere around here. Okay. And then in X direction, it goes 10 meters here. In Y direction, it goes 5 meters. The Y is this one. And in Z goes 4.6. So 4.8, starting from 1.6. So that becomes 6 point something, 6.2. Now, if you do create something that the electrodes hang up in the air, so let's do that. Let's say make this one 2.8. What will happen, I'm just deliberately making something not correct. It gives you an error that it's not working. So it can happen by default values too. If, for instance, the recipe is not able to find out the bounds from the electrodes. If you have a grid or something really looking like a tank, it's easy. But if you have a bunch of electrodes inside the tank, bunch of on the outside and stuff like that, it will be really difficult for you to figure it out. And the default values might not be correct for you. Then you have to change that. Additionally, you can make sure that the electrodes are inside the tank. And this time you don't need to select the buried option. The buried option is only for when you do a surface or a borehole measurement. But for tanks and cylinders that are bound, you can just simply define the mesh differently, and your electrodes will already be inside the tank. So let's say start from -1 in here and -1 in here. -1. And well, it gives me an error. X coordinate of an electrode exceeded tanks. Okay, let's see, make this 5, 12, and 7. Now I don't see any electrodes in here, right? Because now the electrodes are within my tank. So again, for this modeling, region mode, and now you can see the electrodes inside the tank. So when you have like buried electrodes in a tank, you can do that. So I'm going to create some anomaly in here, it doesn't matter. And add region and give it like 20 ohms and exit mode. Again, the anomaly is in here. And for model, I don't know if you have a sequence, so I'm gonna try that. Go to custom sequence, add a sequence, sorry. Import. DC3 tank, okay, there's no sequence, so we just use a default. I thought we had sequences. So you do forward modeling in here. Again, you see, now it tries to figure out where are the electrodes, but unfortunately, this is a non-uniform grid, and you can see the lines are all hectic in here. So don't worry about that. It'll fix up in the inversion, and then you just invert that. Okay, and we had a grid, and this is how it should look like. And again, it's one thing that you notice now you are seeing the electrodes. It's because Resipy tried to cut the mesh to the bounds of the electrodes. If you don't want that to happen, you go to do not crop the output and invert. This time, it will not exceed all the way to infinity like the other time, because your mesh was already bound to the definition, to the boundaries that you defined in the mesh tab. So that's the difference between the tank or the cylinder versus the half space. Your mesh is already bound by your definition. There's a question that says, what if you acquire a single 2D line in Schlumberger kind of acquisition and you get the apparent resistivity in a flat topography? How do you import and invert the data? That is a 2D line. So you do a 2D inversion. And that was covered in the previous webinar. All right. One other thing you can do is exporting your mesh. So you do click on Save Mesh, and you can export it in VTK format or .dat format. So you have to define the format. There is no option to select it in here. So I'm going to call it export mesh, export the mesh .vtk, and save. Now it is exported, and if I go back into my ParaView, so I'm gonna stop sharing here and reshare back my entire screen. Then you can import this exported mesh in here. And this is your tank mesh that you had. And it doesn't have anything except parameter, cell type, XYZ. There's no resistivity. Okay. That's how it looks like. So you can use this mesh in another software. I don't know, maybe PyGimli or any other software that you have that you want to create the mesh with Resipy, if that helps you to create a mesh. All right. What else? Okay, another option that you have, and it's very helpful in my opinion, is creating a 3D survey from individual 2D lines. So not always you can have a full 3D setup, and to do that, let me reshare back my. Somebody is asking, how can we update to the newer version? To do that, you have to go to our GitLab site, or once you download the old version, it will get a pop-up message will pop and allow you to go to the download page. So I'm gonna put the link in the chat to how to do that. There we go. So that's a link that you can get the latest version for Windows or any other one. Okay, 3D from 2D lines. All right, you click on 3D, inverse, and here you will check 3D survey from 2D lines. Again, you will have to import files, and you have to define the file format, and then you have to define a line of spacing. This is not really important, it's just the default to be there. We can later on in the electrode XYZ define the line of spacing or any kind of grid we like, and then select 2D lines. This is the most important one. So click on the select 2D lines and go down all the way to DC. Let's do this one that says DC 2D pseudo 3D synthetic. Okay, so if you click on this one, go to data, there are two lines, line 1 and 2. You click on them, select them, and open. So it looks like that. then you have to import the electrodes. In there, you have the lines that elect in the same folder, DC2D, pseudo 3D synthetic, and open. And now if you go back, it will show you how they should look like in 3D. And if you go to the mesh tab, you will have the mesh correctly in 3D format for you. Okay, so this will allow you to have longer 2D lines if your cables are not that long to create a full 3D survey, and create a 2D from 2D line, create a full 3D inversion, and then you can invert that. Okay. And the problem here, if you notice, is that it is 3D, right? But because it was from 2D lines, you don't have much sensitivity outside of the electrodes. It looks good, but here there's nothing. If I show the sensitivity map, you can clearly see there is basically very, very low sensitivity outside of whatever their electrodes. So you can't always use this option and give you really good results. It's always iffy. The best option, in my opinion, if you have 2D lines, is using the pseudo 3D. I don't know if I have covered that before, but I'm going to go over it really quickly. So for the pseudo 3D, you will still show the lines in 3D format, but only the area below the electrodes, and don't meshing around the part that you don't want. So you click on the 2D and pseudo 3D, and again, import the data from the DC2D pseudo 3D synthetic data, 2 lines, open, and in here you import the electrode lines. And for this pseudo 3D inversion, unlike the 3D, you could have any combination. This line number and electrode number is really, really important. If you mess this up, it will not work, because it actually just assumes there are individual 2D lines fully straight, nothing, no bends or no nothing inside the lines. And therefore you need to really know the correct line number and the number of electrodes. You can have any number of electrodes in one line, it doesn't matter. The orientation of lines versus each other doesn't matter. The topography of individual line doesn't matter, but you need to define what line is what line. And that should follow the number of data that you imported. So each line is one individual data that you imported, okay? So now if I go to the mesh, now everything looks like a 2D meshing scheme compared to the 3D. And if I create the mesh, it looks like that. And you don't have any regions in here, and it's much, much faster than a 3D inversion. And you don't have to be really worried about the sensitivity outside the boundaries, because it's actually not shown in here. And you just seeing visually wherever you have the sensitivity you need to have. Okay. Questions? There's one question that does changing the electrode, the spacing, eliminate the noise or not? No, it doesn't. The noise is different than that. Can you use UTM coordinates for X, Y, and Z? Definitely. Yeah, that's one of the good things about UTM, because UTM is in meters. You can use UTM, and then you can also export the mesh in UTM, and then use it in any GIS software if you want. So, okay. The time-lapse inversion for 3D, let's try that. So again, 3D inverse, click on the time-lapse. Like 2D, you have to import multiple files. So we're going to the example, DC 3D time-lapse borehole. Let's try that one. Data. That's a lot of data. I hope it works. Looks like it's a very complicated problem, so I might not do that. We don't have that much time. Again, looks weird, right? So you import the electrodes. Those electrodes were defined previously, so they had the buried flag. If you remember from the previous webinar, in addition, in that Excel file, in addition label X, Y, and Z, you can actually have the buried column. And for the buried column, whatever row that you put 1 for, that will be buried. Whatever row that you put a 0 for, that will be an unburied electron. So surface electron. Okay, you can see that this looks like this, bunch of boreholes and a bunch of surface electrodes. And then this is a half space. You don't use a tank for this one. I'm gonna create a very large mesh. So what was the electrode spacing? 1 meter sort of thing, right? So I'm gonna like 2 meters, 5, and create a mesh. All right, that this is a pretty big mesh. Hopefully that runs fast. And for the time lapse, you have the option in the inversion settings, advanced tab, to do something called a parallel inversion. This will, if you have a multi-core CPU on your system, 8 cores, 16 cores, whatever, it will invert individual data sets on individual cores. For time-lapse and batch only, it doesn't work for one single survey though. So in here, my computer has, I think, 4 or 8, so it will invert 8 at one time. So it will save you a lot of time. The only downside to that is it might not show you the individual progress format, except the first file. Obviously, the first file is different. All right, this might take a while, so I'm gonna kill it and add some noise to it. The noise are A weight and B weight in here. Because I killed the task, it's now giving me an error. Didn't have done it. Let's answer some questions. Have you documented the accuracy of this algorithm with accepted models? I don't know what that means. What about topography beyond the extent of the electrodes, say the tank mode? Yes, you can add that. I will show you how to do that. All right, so this seems to be dead. Sorry about that. Let me reopen the software. Will this program work for only dipole type surveys, or can it do RIP, reconnaissance IP? What is reconnaissance IP? I don't know what that is. No, it can work with pole dipole, pole, or any other combination of sequences that you have that is not a actual like Wenner or Schlumberger. They're not standard. You can't have that. It's no limit to that if that's reconnaissance IP format. Okay, go back here. Share the screen. Let's do a simpler time-lapse survey. Maybe 3D time-lapse protocol. That looks like easier to work with. Why do you have separate electrodes? Okay, create a mesh and parallel inversion, and then invert that. So the first data set will be shown, but the rest of them will not be shown. All right, so this is now the the first file, basically the background file. So you will not have the difference between each files. To do that, you go to the second file, and then a difference now in percent is added. So it will give you the difference from the first or background data in percentage of resistivity, basically 30% less or 15% more. And you can do that for another file as well. Okay, the rest is basically the same. So how you cut it, how you show it. The question was that, can we import topography points that are outside of the electrodes or the mesh? Basically not the same. Yes, you can. To do that, you will use this part, the second table in the electrode XYZ topography tab. So you can define any points that is outside of the, not an electrode, not outside of the mesh. That's not an electrode. So the topography in here is defined on the electrodes. In here, you can have topography in between the electrodes, but you can't have a topography point way outside of the survey. That doesn't work. It's not going to show. If it's in outside of the bounds of the electrodes, it's going to be outside of the region of the interest on the mesh and not going to be shown. The Resipy will basically cut it. But if you select this, do not crop output, it might be shown, but I don't know what's the benefit of that. Okay. What else? There's a question. I have the 3.4.2 version installed. If I do update, I have to cancel the 3.42. You don't have to cancel anything. It's all free, and you can have all of them on your computer. There's no installing. It's a standalone software. Okay, so what are the things that we have improved in this version compared to the previous versions? One of the things that have been improved is that now the pseudo sections are much more accurate than before. If you have topography, the pseudo section will follow the topography. If you have buried electrodes, the pseudo section will follow the buried electrode. Just to give you an example, I will share one of complicated examples that I have in here. So this is a format of file that you have topography, and you can clearly see the pseudo section follows the topography. This is one of the very good things that have been added. I have other examples in here as well. I can open. My share is still loading. You're not seeing my screen, right?
Correct.
Okay. I don't know what's going on. Let's stop the share. All right. Do you see it now?
Yep.
Okay. So what I meant by the topography following the pseudo section following topography, this is such a weird example, but you can clearly see that now the pseudo section clearly follows the electrodes and the topography. That's much nicer. Prior to that, you couldn't see that like this. If you had buried electrodes, you also can see that. And the contouring probably doesn't work here. You see, contour looks like something like a spaceship, so you shouldn't do that. That goes with the Delaney 3D capability in the inversion tab for 3D inversions with topography. That doesn't work either. The meshing has gone much better. We have added the volume calculation in the inversion, which is nice. The time-lapse inversion now only compares the time that you want with the background. And I mean, that's how time-lapse works. But prior to this, what we used to, what was finding all the data points in all surveys that match throughout the whole time-lapse survey. Let's say if one time-lapse survey doesn't have the certain point, all those data points will not have that point. But now only the background and that time will not have it. So it will save you a lot of data points in between times instead of just making a matching survey points for all of them. Instead of all the files having, let's say, 100 points. One can have 200, one can have 50, depending on how many of them match with the background. So that's another advantage. A question is, where can the current input be modified? What is the default value? You don't put the current input unless you're doing a custom import file. In that case, you can do the current in here. So you define a column that is your current. You can define a column that is your potential and your A, B, M, N, and then you can import it. But if you're using any standard files such as bird, syscal, then you don't have to define anything. If you are doing a custom, yes, you can define. RIP consists of a single current. Question is a current bipole around which many randomly spaced receiver dipoles around the current bipole. So, yeah, I think that is still a 4-electrode configuration. So for any, you can use this custom parser, obviously, and your current your single bipole current can be any A and B. And if it's a infinity, one of them, you put 9999 in there for it. And then your M and N will be the individual potentials. Yes, you can do that. And it doesn't matter beyond a grid. All you have to do is go back in here and then for each of those electrodes, not the poles, dipoles, electrodes, define their X and Y and Z values based on their number. That's all. How can we do the same through API? Okay, that is a big question. Let me show you some examples of the API. So I'm gonna stop sharing again. Hopefully it's not gonna crash. Okay, this is our GitLab site. I am going to show you some examples of Jupyter notebooks. If you go there, you have the Jupyter notebook examples, and there are so many examples in Jupyter notebook that you can just pick up, and they're well explained inside them. Let's say do a 3D advanced mesh one. I don't know what that is, just clicking on them. It tells you step by step what are the functions that have to be imported, what are the steps that you have to do, and you will basically get an idea of how it works. So all you need to do is to do a so for instance is this one, right? So this is the Hillock example. You're importing the proper stuff. You have to install recipe through pip install recipe in a conda environment, importing NumPy, PyVista, and then everything goes well. It tells you that everything has imported correctly. Then you can define your synthetic XYZ coordinate for the surface, then the block. So it's basically Python programming mostly, but there are certain functions that you can use to benefit from recipe capability. And those functions are project, for instance, that's the class that you define for your project. Electrode, if you don't, setting the electrodes, basically, if you don't know what these functions are, you can go to our documentation, which is this one, documentation and examples. And in there, in the API reference, you can look at them and get an explanation. Additionally, you can use the help function of Jupyter Notebook. So help parentheses open the function, parentheses close, and that will give you some clue of what's what. What are the input parameter, what are the return parameters, and so on. So that's how the API is. I highly recommend that if you want to do the API, definitely going to the examples and look at the examples. So for instance, creating a 3D survey from 2D lines. Again, you import the needed importing, create a project, create a survey from the files you have, importing the electrodes. This is all basically those buttons on the GUI. And then create a mesh, define a characteristic length, invert it, and we'll give you what you want to look at. So that's how in the API works. With PyVista in the API, you get a pop-up window that you can do all those, navigate through the basically the block, inverted block. But for cutting through it, you don't have those buttons anymore. You have to define them before creating your result. Okay. So let's see. Any questions? Okay, sorry, I meant how can we modify the input current through API? Through API, everything is a data frame, and your data frame has all those inputs that you want. Modifying the current in the API is just the Python-based work. Let me show you an example. Stop sharing this one. Let's create a Jupyter notebook. So yeah, let's run one of the Jupyter notebooks.
Yes, well, Sin is bringing that up as a reminder for folks that since we are kind of starting to close in on the end here, if you have any last minute questions, don't hesitate to throw them into the Q&A block.
All right, so this is one of the notebooks that has the topography. So I'm just gonna step by step just run it, right? And
the screen share isn't popping up.
oh, really?
Yep.
Looks like when you stop sharing and sharing like multiple times, Zoom crashes. So now
It's a great system.
if it says it's still loading, so I'm gonna stop it and probably it's gonna crash. I will rejoin. All right. Do you see my screen now?
Yep.
Okay. So this is one of the notebooks I opened. So you basically run the importing and everything, and then you create a project. This is a project from a syscal file that does have some those inputs that this specific audience was looking for. So I'm gonna add a cell in here, and if I in here type down k dot surveys 0, you always need that data frame, and run that. So you get the data frame that gives you where the A, B, M, N are, what is the resistance, if there's SP, IP value, and so on and so forth. In your input file, you can define how they look like. So this syscal.csv file, all right, it had the ability to change them. If you have a custom imported file, all you have to do is have all of these available for the software. So if you calculate, if you have the input voltage, if you have an input current, you have to calculate the resistance. Do it in Python, put it as a resistance in this column. That's it. That's how you change the input current. Does that make sense? There's another question. As far as my understanding, through the API, if we had to add a circle elliptical anomaly 2D we need to import an array of discrete points lying on it. Is there a more elegant solution? I don't follow what you mean by that. The next question, what do the parameters A and B mean for inversion? Okay, this is A is your current dipole, first, positive or negative, doesn't matter. B is your the other current dipole, positive or negative. M is your potential, one of the potential dipoles, and N is the other potential dipole. Now, if you have one that is pole dipole or pole, in your electrode definition, not in here, not in the DF that you're seeing in here. In your electrode definition, you will have to, so if I do elect in here instead of DF, in your electrode definition, for the X location of that, you should put 9, so many nines. And if you have a pole, for the location of that, one of the poles, you put 9999, the other pole will be negative 9999. So that's how the dipole works. So A, B, M, N, they have a number associated to them. That's the number.
Then I'm wondering if they might be referring to the A and B weights.
Oh, okay. That is the inversion error weights, and the higher the B is the percentage error in your data. A is the offset error. So if you have, let's say, 5% error in your data between normal and reciprocal, you put 0.05 for B. Another question is that, is it possible to compute the difference between multiple surveys inverted on the same mesh, or only if they are imported and inverted together as a time-lapse survey? I think what you're saying is exactly the same thing as time-lapse survey. So that's what we're doing. We're computing the difference between multiple survey inverted on the same mesh. That's all what we do, and that's called time-lapse survey. No. Okay. I still don't know how to answer that. How can we add a circular anomaly? Oh, to do that, so once you create your mesh, so let me create my mesh in here. Let's say this is the mesh, right? So everything, I had to run everything. Okay, sure, okay, that's not important. Import electrodes and create a mesh. Okay, this is my mesh, right? In here, if I that mesh .df, so that's the data frame for the mesh. So you have the X, Y, and Z of individual nodes on the cell. Okay. Sorry, the center of each cell in here, right? This is your X, Y, Z. If you want to create a circular anomaly in here, you have to figure out how to select them in a circular manner. So you have to define a function that will select based on a circle on this. That's how you define it in the API. Again, this is not a function that we define. You have to create your own function to select the right X, Y, and Z's in here to create a circular anomaly. Basically, selection box. Okay, and then invert, similar to the GUI, you see, and then show results. We'll show you the results. So that's how the API works. Okay.
All right. I think we are at time here. Thank you, Senna, and thank you to everyone who attended today's webinar on our second webinar on Resipy. Please respond to the webinar follow-up email. They'll be getting within the next day or two. Let us know what you liked, what could be done better, any suggestions you have for future webinar topics, as well as keep an eye on our social media for posts to register for future webinars. I know people have been asking about the video recording for this. They will be up eventually. Just have to go through an editing process, and it's pretty much just Lori and now me who's gonna be starting to edit these. So we'll have them up eventually. Just give us a little time to work through it. But yeah, thank you all again for attending this webinar, and thank you again, Sina, for taking the time and taking on Jimmy's section as well last minute.
Yeah, no worries. If you found bugs, please report them. I think I found a couple of bugs myself. I don't know. Yeah, we'll do our best to fix all these, and always please submit your problems, questions on the issues tab of GitLab. That's the best place because the right person get to you and answer them. If you have any suggestions or you have your own part of the code that you created for some specific things, definitely do a pull request on GitLab or GitHub, and we'll look at it. And if it's really worthy and really good, we will actually merge it, because we already have done that for one person who's actually added the function to change the electrode size on the 3D meshes and the API. So we will welcome all those changes. Thank you.
Awesome. Thank you, everyone, and enjoy the rest of your days.
Yeah. Bye.